Okay, so thanks for the introduction. I'm Taylor. I guess we have a lot of people at the controls talk maybe, but whatever. So I'm going to talk today about uniform verification of parameterized systems. So I've got a little bit of a cold, so I'm a little drugged up. So if I say anything that doesn't make sense, just stop me and I'll try to explain. So what we're talking about here, let me just introduce the problem, then I'll give a little bit of an outline. So we want to perform automatic verification of some distributed algorithm. So what we're going to do is we're going to say we have a state transition system or an automaton A sub I and some temporal formula F. And then we want to check for every natural number n that the parallel composition of n of these automata AI satisfies the formula F. So that's pretty abstract, so let me just kind of dig into what AI might be. So AI could be some finite state machine, it could be push-down automata, it could be timed automata, it could be probabilistic like Markov chains. And what can F be? So in general, what we want to be verifying some temporal property. That might be some safety property, and if you're not familiar with what a safety property is, it's just that something bad never happens. Likewise, it might be some liveness property, which would just be that eventually something good happens. And it's often harder to check liveness properties, but there are a few works that can handle more general temporal logics, like CTL star without the next time operator. But what we'll focus on in this talk will just be safety properties, because the majority of works checking for liveness ends up being undecidable, so we can't do it in general. And then all of this is going to be under some synchronization constraints and communication primitives. So what I mean by that is there'll be some restriction between how we can compose the automata, so how they can communicate with one another. And even for finite state automata, there's an old result, this Apton-Cozen result from '86, which says that even with finite state automata, this problem would be undecidable. And they don't even have to communicate, actually. And the intuition behind this is that, well, we're trying to verify something for essentially any natural number n. And the composition of all these things, this is an infinite state model checking problem. So for the outline, are there any questions on what I'm talking about for the problem? Okay. So I've introduced the problem. I'll talk about some motivation of why this is an interesting problem to look at. I'll go through an example of a distributed mutual exclusion algorithm, which is a simplified version of the bakery algorithm that Leslie Lamport designed in the '80s. Then for generally how we would check these safety properties, I'll go through a little bit of this reachability algorithm. And I'll talk about some general abstraction techniques for how we can attack this problem, and then I'll conclude. So to motivate what I'm talking about, we want to look at automatic verification of different types of systems that have an arbitrary number of interacting components. So this might be cache coherence protocols, where we're parameterizing on the number of caches, or this might be distributed algorithms, where we're parameterizing on the number of processes participating in the algorithm. So in the case of cache coherence protocol, maybe we have 2 caches because we have 2 cores, something like that, and we need to verify. In the real system, of course, we're not ever going to have n cores, right? We will have some fixed number, but if we want to verify that whatever design we've done worked for 2 cores or 4 cores or 8 cores or 16 cores or so on and so forth, we could potentially do this type of analysis for all of them simultaneously, and then we'd have a proof that some property holds. So that's kind of a little bit more of the motivation of why we want to do this. Similar examples with distributed algorithms, and I'll talk more about a particular one, the Lamport's bakery algorithm. And the other way this can be viewed, this is one way to attack the state explosion problem. And the state explosion problem, essentially, I guess we can just say that as we have asynchronous interleavings with concurrent processes operating, the number of states we're going to have to check is going to blow up. So this is one way to reduce the number of states that we have to check. And the challenge here is this is an infinite state model checking problem, so we're going to have some sort of abstraction. So for the example type of properties we might want to verify. For a mutual exclusion algorithm, the safety property would be that there's at most a single process in the critical section. And that an important thing to note here, we need to be able to express properties without referring to how many processes are involved in the computation, so that this property is independent of n. So how would we go about proving or verifying that something like this is correct? Well, before we would actually verify it, we'd think about it, we'd maybe simulate it, we'd run it, we'd kind of believe that it works, and then we might try to prove it. So the first pass of trying to prove it, we might do some manual verification. We'd try to write a proof of this. We'd maybe arbitrarily choose n in our proof, then do a proof by contradiction or something, or maybe we have an induction on n, the number of components in the system. And this point that a lot of these mutual exclusion algorithm proofs are by contradiction, that's sort of what we're going to do later. We're going to assume that we do have we've reached a state where there can be more than one process in the critical section, and then we'll show that that's actually impossible. So moving to more automated methods, maybe we'd use some sort of automated theorem prover like PVS. If we tried to apply standard model checking to this, and we instantiated, say, n to 2, and then we generated this composed automaton, and then checked to see if we can reach some illegal state, the issue with doing this is all we've done now is we've showed that it's correct for the composed automaton of 2. What do we do next? Do we increase n and try again? Do we try it for 3 processes, try it for 4 processes? Similarly with the cache coherence example, do we prove that it's correct for 2, and then for 4, and then 8, and then 16? What if we want to build a 1,000-core processor? So the alternative to this is what I'm talking about now, and this is this parameterized model checking. So we'd like to automatically verify for an arbitrarily chosen value of n. So the example I'm going to talk about is this simplified bakery algorithm. So this is an algorithm for mutual exclusion. So we want to get one process at most into the critical section. All the processes start in the initial state, and they're all equipped with this ticket. And the intuition behind this is that the processes are sort of coming into a bakery and they're taking a ticket. And then whenever you come into the bakery, you're going to take a ticket value that's larger than all of the values of everyone else in the system. Upon you, so if it's 5, you'll now get a ticket that's at least 6, right? So that's what we'd have. Upon that, you start waiting in line, and then eventually, after you can enter the critical section if all of the other processes either have not yet taken a ticket, or if your ticket is smaller than all of theirs. So if you come in, you're first in line, and then you get to go right and get served by the baker. So that's kind of the intuition behind this. So this is actually a pretty simple algorithm. This isn't the full-blown version from Lamport's original paper, but essentially, if you're the first guy in, you're happy. So let's say you're process number 24. You come in, you get some ticket value 2. But now if you come in with, if you're the next guy to come in, maybe you get ticket number 3. Maybe you're the next guy, you get 4. Maybe after that, you get 6, just because we haven't really said what value we're going to give to the ticket. So anyway, all of the others up to n are either going to be 0 or they're going to be larger than everything previous, right? And one thing we're going to abstract away, we don't care which process actually is the minimum or anything like that. So that's one thing that'll get abstracted away. And hopefully I've convinced you that there, at least at this point, I don't know, maybe I don't know if everyone's convinced there can only be a single process in the critical section if we follow these rules. So how would we automatically prove this? How would we prove it in general? Again, probably we would assume that there are 2 processes, or at least 2 processes in the critical section, and then we try to get some contradiction that's going to violate maybe where all the processes started, or if we look at each of these rules, we'd see that it violates some of these rules. So what is a composition of processes in general? So if we take this bakery algorithm example, so this would, let's say, be the 2-fold composition, so 2 processes are involved. And each of them needs to be able to look at just the ticket value of the other one. So it might look something like this. So the challenge here is we start to do, let's say 3 processes or or more, we start to have a lot more of these interconnections. And this is how we might wind up with a state explosion. So if we had in, each of these would now have to have a connection added to in, and so on and so forth. So as we flatten this automata, it can get very large. So a little bit of notation for the remainder. So it's just the same that's already been introduced, but Qi is this control state for process I. Q is the finite, the control states of all the processes, and you can imagine that this is a vector. Ti is the ticket value for whatever process, and likewise T is a vector of all the ticket values of all processes. And then Q is a configuration or the composite state of all these control states and tickets. So the way that we're going to think about this problem, we need some nice way to think about this problem. So what we're going to do, we're going to come up with a symbolic constraint to describe the state of the system. So we're going to do some symbolic model checking. And constraints are a restricted class of first-order logic formulas, and all that they're going to represent, it's just going to represent a state of the system, really. So in the case of our mutual exclusion algorithm, the unsafe property would be that there are at least two processes in the critical section, and we can express this in first-order logic like this. Given two distinct processes, they're both in their states both in the critical section. So in general, we can have some, we can quantify however many processes we want, and then have some propositional formula on the composite state Q. So likewise, the initial states were described for all processes. Everyone starts, in some state. And in general, again, it's just a first-order logic formula. One thing to note with the initial states, it is difficult to pose a forward reachability question because if I've described the state of all processes, I'm trying to do forward reachability. I'm like trying to make potentially everything do a transition simultaneously or something. It doesn't really make sense. So this is why we're going to see in a minute why we're going to start from the bad set of states and show that we can't reach them. So the way these state transitions are encoded, again, it's just a first-order logic formula. The way the enter action from earlier, which is where a process goes to the critical section, we would say it's initially waiting, which is that middle state, and if it's if the ticket values of all the other processes are less than it or 0, then it can advance to the next state. So we've got this lambda notation. All that the lambda notation does, it just means that we're giving a value for all processes. So it's a well-defined notion. So this lambda j, you can just interpret this as a for all. So this means that the update, the post state of this transition would be that if j is equal to I, so if for all, if for all j, if we're talking about the ith process, it'll end up going to the critical section if all these conditions held. Otherwise, it'll keep the same state. So we just need some way to define this update in a well-defined way. And then, so given a whole bunch of state transitions, we'll have the composite state transition just be the disjunction of all of these. So for the Bakery algorithm, again, this should be hopefully clear. The bad set of states would just be any state where there exists two processes in the critical section, two distinct processes. And again, the initial states they all start off in the initial state and with ticket value 0. So the step transitions, I guess I'll kind of skip through them, but you can kind of imagine it's just more of the same of like what enter was. Exit is just going to be, if you're in the critical section, you can go back to the initial state, things like that. So what we're going to do, we've sort of got a way to talk about states of the system now. So now we need to we've got a way to talk about the states and transitions among states. So now we would like to see what states can be reached. So the way that we're going to do that is we're going to have a reachability algorithm running from the unsafe states. And this will involve this preimage computation. And the preimage computation, we have an existential over this global state. But in some of these works, we have a nice theorem which would let us say that we can just get rid of that existential, and all we actually need are the existential over the process IDs. So anyway, so don't worry about it too much if you haven't seen this before. And then the way that we're going to describe what states of the process, we're going to have some inductive sequence of these formulas. So we started with some constraint, This is the bad set of states. And now we're going to take this pre-image. We're just seeing which states can reach the bad set of states. That's all we're saying. From what states can we get there? And so we've inductively defined this, but as we run the algorithm, we'll see that we can reach some states in one iteration of this. We can reach up to some k states after k runs of this algorithm. And the system will be safe if we never intersect the initial set of states with the bad set of states or the states that can reach the bad set of states. So I haven't said anything about how we would guarantee that we actually can stop this algorithm. So far nothing has been said about why we would terminate this process. So right now we would just run it for a long time, and then we'd stop. We would never know that the system has truly been verified because we don't know when to stop. So we need some sort of a condition for when we can stop the algorithm, and that would be a fixed point check. And that check essentially amounts to this. If the states reachable in k+1 iterations are a subset of the not necessarily a strict subset, of course, but if they're contained within the previous iteration, then we can stop the algorithm. So all that this means is we haven't reached anything new. So then we can stop, and we could return that the system is safe. And then just formally, this would be how we would check this fixed point. So that said, I still haven't said anything about how we would, so that's a check for when we can quit running the algorithm, but I still haven't said anything about that we're actually going to reach a point where we know that that's occurred. All I've said so far is we can quit if we reach that, but now we need to do something saying that we actually reach a point like that. It's sort of like in controls, the existence of an equilibrium versus actually reaching that equilibrium point. So how can we guarantee termination? So I'm just going to talk about a couple general abstraction techniques without a whole lot of detail. So we have an infinite state model checking problem. Somehow we have to convert it to something that's, essentially we want to convert it to something that's finite state. So how can we do that? So one abstraction that's worked for some safety properties is that we only remember the number of processes in each state. And then we cut this off at some value. So forget about the ticket thing. Just imagine that we just have a finite state machine. And all we're going to remember, so in this case we had these 3 states. All that we're going to remember are there are 0, 1, or 2 processes in any of these states. So this is now finite state, right? So there's only a few, there's not a whole lot of configurations of this. Does that make any sense? Yeah, okay, all right. So then, this type of reasoning can also be used for liveness, and we would remember the exact state of one of the processes potentially. There's some other abstractions where we would combine this counter abstraction with predicate abstraction, and we would count the number of processes satisfying some predicate. We could potentially use this in the to encode that ticket now, and the predicate we could have there is that the ticket value is now less than or larger than all the other ticket values. So we can generalize it to our example. And then there's also a technique called network invariance. And essentially what we want to do here is we're going to prove that one process satisfies some property I, and then we show that if we take another process and compose it with essentially with that process I, if we view that as a process now, if it still satisfies I, we can verify that the whole system will satisfy this property. So for our current and future work, we've been working on verification of these parameterized physical protocols, where this would be traffic control protocols for aircraft or automobiles, which are composed of in-vehicles. So rather than distributed mutual exclusion algorithms like this, we maybe now have a distributed physical mutual exclusion algorithm, where our mutual exclusion property is just that 2 vehicles don't ever occupy the same space. So we're unsafe if 2 vehicles, if we just imagine we're on a line, we're unsafe if we have 2 processes that can get too close to one another. So we'd want to maintain some spacing with this. So we could model these as timed or hybrid automata, and we're working on generalizing some of these abstraction techniques. So As far as the type of tools that we've been using an SMT solver type tool with this problem. And there's some other tools available like this undip tool. But pretty much the algorithm that I went through, this reachability algorithm, pretty much what they're doing, they're implementing this reachability algorithm. So behind the scenes. So to prove that it would actually terminate again, we would have to do something like what I described earlier when I discussed its termination. So I guess that's about it. Are there any questions?
Is there assumption on processing dependence, or does what you say?
So can they communicate in some way, or?
So like a process that arrives later, but it needs another process that will arrive later in order to start execution. So there's data dependency.
So there could be, yeah. Yeah. So I mean, in this bakery algorithm, there is a dependence on the tickets, right? So, the ticket value to actually enter the critical section, there is a dependence upon the other ticket values in the system. So, yeah. Is that your question, or?
So once it enters, let's say like it enters with ticket of 4, but it needs before another person to take a ticket of 10 to exclude.
So in this example, so I am making some atomicity assumptions in this example, if that's what you're getting at. So yeah, so there is some notion of that in here. So in the full distributed bakery algorithm, so that's also been verified automatically with some of these tools. But I just picked the simple one as an example because the other one has some nastiness. Yeah. Does that answer it now, or okay? All right. Anything else? Yep.
So the example you only consider one parameter, right? There's only one parameter that by which we parameterize the problem.
Right.
Can you handle more?
So there is some work on this. So let's say you have 2 different automata, and you could parameterize each of them on, let's say, n and k. And then you could compose all of these. So there's a little bit of work on that. But most of the work assumes that you're parameterizing on one thing, and it's every process involved is identical. Does that answer? Yeah. Okay, thanks.